in engineering companies, we're always going to do optimization to find the best designs. Bayesian neural networks are one of the key things, can be used and integrated throughout optimization studies.
Where does AI fit into this kind of optimization problem task?
In simulation, it can take 3 hours or 3 days to run a simulation sometimes. So at the end of the day, you have to be having some intelligence to pick the cases in this design exploration or this robustness and reliability study. And that's really hard to do.
Is there kind of a guidance that you could give to the audience in terms of how much data do I need?
It depends on how nonlinear the problem is, depends on how many inputs you have. Our barrier between computer science and mechanical engineering is going to continually shrink. We're not going to be replaced, but we will have this in our tool belt. I would start there, take 1 month to learn general things about machine learning. Somewhere around the 6-month mark, you'll start to feel like it's making sense. That's where you can be your own guide. You know, we're the bottleneck as engineers. Anytime you're doing an optimization study, HEEDS is an excellent choice.
Cool, ladies and gentlemen. Justin again on my podcast. The last time you went on my show was episode 85, October 2022. So it's been a while. You've achieved much more since then. You've written a book. You've done a bunch of other things. We're invited into a couple of impressive keynotes. So Justin, welcome to the show.
Thanks. You've done a lot too. I've seen a lot of the work you've put out there, and it's very exciting. I think, yeah, it's weird. It's already 2024, and it's been that long since we've talked. But yeah, I'm happy to be here, and I think we laid out some good stuff to talk about today. So
definitely.
Thanks.
The topic for today, at least, will be AI optimization or optimization in general, but kind of from a historical timeline. Can you maybe give the audience kind of an introduction of where does AI optimization or optimization itself and then AI plus the optimization bit for simulation in particular sit kind of in a timeline when we have a look at all these methods that came out to help engineers solve problems?
Yeah, right. There's a certain historical moments if you're in engineering where you've seen advent and uptake and traction in machine learning methods. So yeah, back in 2018 and 2019, you saw a lot of studies where people were literally running thousands of simulations and just using machine learning to interpolate between them, essentially, which is still useful, but man, that's a lot of data, right? And I would say from then until now, it's gone down at least an order of magnitude in terms of how much data you need to train a machine learning model. And then of course you have the advent of PINs and physics-informed neural networks, which are these types of methods that can work with less data and be used in a more extrapolating type of way outside the space where the data was trained, strictly speaking. But one thing that is kind of a challenge inherently is optimization problems. Because on one hand, in engineering companies, we're always going to do optimization to find the best designs, right? So we know that data is always at hand, in reach, available, and we could do machine learning on it. But it's kind of a fundamental antonym, challenge, difficult with optimization problems, because not all the variables are given the same amount of attention when you generate samples and generate your data set. So for example, I'm doing a survey of a bunch of questions that people will take around the world that will indicate whether or not they have like heart disease or not. You know, I'm going to ask all ages, all ethnicities, all global regions, all types of people, so that if anyone takes the survey, there's probably several people of similar sort of demographic that took the survey, and it would be good, you know, it'd be a good model that was trained on relevant data to apply for that person as well when someone goes to take the survey in the future and see if they have heart disease or not. So similarly, when we do our simulation studies, you know, we design an airplane, for example. Well, if we do optimization, we may not care about 30% of the variables, right? If we're maximizing lift and minimizing drag, some of our geometric variables just might not be too sensitive to that result. So when we generate the optimization study and design the thing and have all this simulation, we may have 30% of the variables that are completely unchanged. So this is the opposite of the survey scenario for this cardiac disease scenario. This is not a good situation for machine learning because we don't have samples from all kinds of values for all the variables. Just generally at a high level, that's kind of a challenge. So within the last year or so, though, I think there's been plenty of cross-pollination from what you could call mainstream tech, mainstream machine learning, into the engineering disciplines and domains like aerospace, mechanical, thermal, our world of computer-aided engineering and test. And so now these methods like Bayesian neural networks can be used and integrated throughout optimization studies so that people can still take advantage of them and speed up their processes, speed up their optimization cycles, even if their data is imbalanced, is what we could call it, because sometimes you would not sample every parameter, every variable equally, so it goes by the name imbalanced. So I'd say, yeah, recently this is starting to become attractive, and it's great because everyone does optimization.
Yeah, that makes sense. Where does AI fit into this kind of optimization problem task? Like, why AI? And is it really AI at the end of the day? Like, how much of AI is actually AI? If that makes sense.
Yeah, right. Because, yeah, the hierarchical thing, AI, a subset of that is machine learning, a subset of that is neural networks, and a subset of that is deep neural networks. So we'll talk AI/ML to be inclusive, but a lot of this that we're actually going to talk about in terms of the technology is just machine learning. Bayesian neural networks are one of the key things because they offer confidence levels, so to speak, as a sort of feedback after they're trained on how accurate or good they fit certain data sets. So you can use that as like a metric for being judicious on which cases are really accurately modeled and captured by your neural networks versus which ones aren't, and therefore you should do simulations on. So how does it play a role, right? I think there's a good case study we can just talk through. Sometimes it's overwhelming. You can talk about all the good things that machine learning can do for us, all the use cases, but sometimes it's interesting to just pretend you work at an engineering company and go step by step through your tasks. And when you do that, you can see machine learning can help you at several of these stages now that we've had the advent of these methods that are for us, machine learning methods. So we published this sort of this example in a chemical engineering conference a couple months ago, and it was for a bioreactor, kind of like a mixing vessel where we really care about processing chemicals and designing the mixing vessel in such a way that it would saturate oxygen, mix appropriately, things like that. So the first step was optimization. So just perform the best mixing vessel possible. That we can do, right? So in our normal way of doing things, we'd have a simulation that would run. It would change the geometric variables iteratively so that it would keep finding the best mixing, things like that. And you can do this with our software at Siemens HEEDS, but we can keep it very generic and agnostic for now and just talk about the technology because I think that's more inclusive. And so how it works in that case when you're doing an optimization task is you run a simulation or a number of simulations, and then you train your machine learning model. And this is all throughout the optimization cycle. So say you're doing 500, you're budgeting 500 simulations to run an optimization process. So let's say you run 100. You can train a machine learning model on those 100. And then when you go to run the 101 point in the study, because you have some optimization algorithm guiding you, telling you what probably is the next best case to run to maximize your cost function and satisfy your design objective. Well, when you go to run that 101st point, what if you had a Bayesian neural network that was trained on the data so far that was generated, and it could tell you a prediction for the results. So you could not run the simulation, and it would give you these confidence metrics at the same time. So it could quite literally express how confident it is based on the points used for training so far that it would accurately predict that point. Well, that's beautiful, because then if I run my 500 simulations, if I run my 500 design points, I may skip 20% or 30% of the simulations. And that's attractive because, as you know, in simulation, it can take 3 hours or 3 days to run a simulation sometimes. And this machine learning model will make an inference for you in 3 seconds, literally. In that study, it was between 1 and 2 seconds wall time where the Bayesian neural network would make the prediction. So yeah, in terms of the first step of the process, find the optimal design, we can use machine learning to skip a lot of those designs. And it's really just about monitoring the process, right? Just calling the neural network to be trained, make a prediction, some automated way to judge if it's a good or bad prediction, and then proceed with the simulation if it's a bad prediction, or just move to the next point. The neural network did a fine job.
Yeah, that makes sense. I was wondering about the Bayesian neural networks. You mentioned this kind of as it kind of is a natural thing to do. It's one of the maybe only solutions because the way we speak about it, right? Maybe you could explain to the audience what is a Bayesian neural network to begin with, like how does it work, and then are there other alternatives in terms of neural networks, especially when we talk about CAE or enhancing simulation using ML optimization?
Yosef, we're going to have to edit this and backtrack because I don't want to reveal too much more than what I've said as far as like how it works. And then I also think there's other stuff that people could do other than BNNs. So I don't want to make it sound like it's only BNNs, but yeah, I don't fully know and I don't know. I would worry about IP as well. So is that okay?
That's fine. Okay, let me try to find the next question. Okay, you talked about kind of this mixing example, right? Let's say from a practical example, can you walk us through a general example how an engineer would run through such an optimization study? Like how do I pick my variables as an engineer? Let's say I'm completely new to the field, right? First time I'm using a tool, for example, HEEDS, which we'll talk about a little bit later. How am I going to approach a problem like this? Where do I start?
Sure. So there's still some level of domain-specific knowledge you would need to have, but no problem if you're not an expert. So in this case of a mixing vessel, we care about the mixing and saturation of oxygen through the chemical that we're processing in and out. And in that case, we care about turbulence, we care about separation, we care about flow patterns. So if you look at the primary direction the flow is taking through this cylindrical vessel, you have these impellers or fin-like structures inside that are spinning along an axle. So you could change the geometry of those impellers. You could change the internal shape of the mixing vessel, for example. And in this case, if you're new to it, new to the area, new to the domain, then you could throw all the parameters at the optimization model. And that's okay, but it would be better if you had a more physical intuition of the system, because then you could narrow down to fewer parameters or make derived parameters like Reynolds number. In that case, instead of using velocity, fluid property, and length scale to define Reynolds number, using all of them in a study, you could just use Reynolds number if you understood that existed. So in this case, you provide inputs or independent variables for the design, and then there's an optimization algorithm that will look at how changes in each of those parameters affect the cost function or the objective, which in that case could be to maximize mixing, to minimize the strain on the fluid, to minimize the power input provided and necessary to spin the thing. And in that case, it will just iteratively generate results, look at the relationship of inputs and outputs, and then project to you the next set that it thinks would help find that sweet spot.
Do I need to find, sorry, Justin, do I need to define the cost function myself, or will the optimization algorithm do that for me?
Usually you have to define that up front, and it can be very, very simple because it's not necessarily like a complicated function. It's just very primal sort of things. Maximize the lift of my airfoil, minimize the exhaust of my combustion system in terms of pollutants, minimize the pressure drop through my system where I'm pumping fluid through it. Something like this. So they're pretty simply expressed, but then it can get compounded pretty quick if I'm having like 3 of these things competing against each other. Then that's where the nuance comes in, where a numerical approach to optimize the system is going to be better than complicated intuition applied to the problem.
Absolutely. You talked about inference a couple of minutes ago. Is that one of the most promising areas that you can say, okay, instead of running a bunch of simulations, let's say 200 simulations, I can run like a fraction of that because I can do like real-time inference based on my previous data? Like, is that the most promising thing for you in regards to AI? Because a lot of people are saying AI will substitute engineers. Some people say it won't substitute engineers. Is it actually a substitution at the end of the day, or more like I'm enhancing my existing tool stack or engineering capabilities by being able to reduce my number of tests and or simulations? Is it the most promising thing that you see, Justin, in the area happening right now? Or is there something else?
it's the stage or the step in the process where everybody sees the value, right? Because at the end of the day, you need to generate the data, which can be a guided process. You need to train the model and decide and analyze what's the best model to use and how to safely apply it afterwards. But then when you go to do the inference, that's where people see a typical cycle. It may take a week, take an hour, because this inference is immediate. It's in a fraction of a second. And even this case study that we're talking about, right? Only the first step is to optimize the design of this mixing vessel. So we can continue this case study, and you can see that machine learning with sampling approaches, with optimization, for us in engineering disciplines, it can keep going. There's more teams and subsequent steps in the process that really benefit from this. Because let's say I come up with the best mixing vessel design, right? Well, I'm not going to just immediately produce my mixing vessel and start manufacturing it based on that outcome, right? I have to then maybe, for example, take that optimal design, which I came up with at nominal operating conditions, and I would normally do like sensitivity study, robustness and reliability study, basically run that design through a number of other scenarios that are possible to make sure that it would safely operate in all of those cases. Right? So if I was designing an aircraft, I could come up with the best design for the turbine, but then I have to make sure that it doesn't fail with different ambient conditions, with different temperature constraints that may happen in that part of the turbine based on things that could change upstream, if different parts break, if different parts start performing differently. I really have to make sure it's safe under a wide variety of scenarios. And that's another area where machine learning can really help. And this is something in HEEDS, but in general is a very general possibility for value for us as engineers. In this scenario, I say, okay, I come up with the best mixing vessel design. Let me simulate every other scenario possible to make sure that it's safe. Well, you can't simulate every other scenario, but there are probably thousands of scenarios that are reasonable, but you may only have budget to simulate like hundreds. So at the end of the day, you have to be having some intelligence to pick the cases in this design exploration or this robustness and reliability study. And that's really hard to do because you could have ambient conditions change, other performance-based things in the system change. So there's a lot of possible variations that could happen. And that's one area where machine learning helps a lot. There's this approach or this technology called active learning, which is a way to pick those cases in your large permutation, large design space of things that are possible. And it allows you to pick them dynamically via a machine learning model so that you can most accurately fulfill sort of your objectives. So what does that mean? Let's give a concrete example. If I want to maximize mixing of my design, and I want to ensure that it works under a wide variety of other ambient conditions, well, then I can specify that I have a budget of like 100 simulations. I'm willing to run 100 more simulations to satisfy this idea that it would still be accurate and performant, not accurate. The design would still be performant and efficient in this other vast space. So normally I'd have to pull out like random sampling or uniform sampling or Latin hypercube sampling out of my tool belt to sort of project how I spend that 100 simulations. But these are kind of insufficient, and they are done in a weird way, not a weird way, but like a less ideal way where you specify the cases you're going to run up front, then you run all the cases, then you analyze the data. And that's not great because then you're not leveraging what you learn along the way. So with active learning, or this feature in HEEDS called adaptive sampling, what you're doing is you're running batches of them, which could be in this case 10, if you have a budget of 100. You would run the 10 cases, you would train a machine learning model, and then it would look at what 10 simulations could be run next to maximally learn. And that's very valuable when you do that 10 more times or 9 more times to complete the 100 cases that you've run, because now you've basically algorithmically tried to learn as much as possible in your space without just kind of archaically saying, I'll uniformly sample all the possible scenarios with these discrete points. And furthermore, not to make it too in detail or technical, but you have the opportunity to specify your objectives. When I run these 100 cases to learn about every other scenario possible for my optimal design, do I want to prioritize finding extreme anomalous behavior or edge cases where the results tend to change dramatically. So it could be like a safety thing. If this was, again, the airplane example, do I want to focus on where I start seeing very crazy pressure ratios in my turbine operation and think that something bad's going to happen or catastrophic event? Do I focus on budgeting my 100 simulations to identify those cases? Or do I budget them to just get a global representation? You know, this is a huge space, as I've said a bunch of times. So maybe I just want a good global fit in terms of being able to learn throughout the space pretty well what happens under a lot of wide variety of scenarios. And there's other ways you can tailor sort of this objective on how you budget the 100 simulations. But I mean, this is a scenario you've probably heard of a million times, right, Joseph, where I have thousands of points I'd like to consider. I can only run 100 simulations. How do I do that? Design of experiments, design exploration. It goes by many names, right?
Yeah. I'm wondering, when we talk about data, is there kind of a guidance that you could give to the audience in terms of how much data do I need? And we talk often about big data and machine learning, right? What does big data mean in the realm of engineering? Like, how much do you actually need to get started, and how much data is enough data? Does it depend on the data type? If it's 3D, if it's tabular data, like how do you approach this in general?
So that's a good question, because essentially I just finished long-windedly describing a technology. The technology enables you to sample a space really efficiently. So, you know, they go hand in hand, right? You're always going to want to know how much data you need, and no matter the problem, you're never going to know for sure until you generate all of it and look back in hindsight on how much it did or it was or was not enough. So really the solution is a sampling approach like this, or some advanced sampling technique that will dynamically learn as much as possible. It'll help you learn as much as possible from a discrete amount of simulations that you're saying you're willing to run. But to answer your question in a different way, it depends on how nonlinear the problem is, right? Machine learning is nothing but a regression correlation mechanism between independent variables, between results and inputs, whatever you want to call it. Depends on how complicated the relationship is, right? If I have a linear relationship of pressure and mass flow rate, then I don't need that many samples to pin down that linear curve, right? Depends on how many dimensions I have. If I have 3 inputs or if I have 30, that's very, very different in terms of how much data I need, even if the relationship is linear in both. So some people say twice the number of inputs plus 50 if you're working with any sort of like spatial simulation data. So if I want to make a machine learning model that can predict, you know, my CFD results through a plane section or like a 3D section, then maybe a reasonable thing is, well, I have 5 independent variables. So times 2 plus 50 is how many simulations you should expect minimum to start with. And that's a reasonable rule of thumb. But like I said, it really depends on the nonlinear nature of the data, depends on how many inputs you have. And also, if you don't know and you don't have a confident back of the envelope guess to approximate how much you would need, then you can use advanced sampling approaches like this one that we've described that will help you just get the most out of however much you're willing to run.
What are some of the metrics you're having a look at just in terms of like being able to trust the ML model, like optimization algorithm in this case?
Yeah, that's where, in my opinion, it's the most fun. It's the most fun job possible, in my opinion, is the people that know the domain knowledge and some about data science and machine learning, and they get to do both. Because in reality, the best way to judge a case and judge the model, the machine learning model's ability to predict and capture that phenomena, is to make metrics that come out of your domain knowledge. And that's what's super fun. I remember, I'll give you a more concrete example. We did a study for CFD through an internal combustion engine. And we wanted to make a machine learning model at the end of it that could predict the full flow field inside of it. And so in that case, we start at the thing we care about as the result. The main thing we're doing is to characterize the mixing. And then we backtrack one step and say, well, that really depends on the flow separation. And then we backtrack one step and we say, what impacts the flow separation? Which geometric design variables do we have that will directly influence the separation, which will influence our result. And so in that case, that's how we posed our machine learning model study. Is we said, let's characterize the mixing, and let's structure the experiments to train on a certain number of cases that have a little mixing, moderate amount, and a heavy amount. And then we'll evaluate and test the model on some of the same, some mid, min, max, sort of all across the board mixing. No surprise, it did okay, did fine, because it trained on a lot of similar cases that it tried to predict, evaluate on. But then we said, let's make it harder. Let's only train the model on the cases that had very little separation, therefore very little mixing. And then let's evaluate the machine learning model's performance on the high mixing cases. And in that case, it still did fine. Mm-hmm. So now I have a lot more confidence that when I give the model to somebody to use, and I say that, okay, this only works in this RPM range or in this separation angle range. So that was really fun, because it can give you this insight of both the physics and how much physics can be captured in the machine learning model. So to me, to answer your question in a succinct way, when I go to set the metrics to evaluate a machine learning model, they may be boring things like, absolute error or, R squared, or these standard statistical sort of measures to evaluate a machine learning model. But the formation of the experiment, the training, the picking of which cases are for testing versus training, all of that is the conclusion to me on how well a machine learning model can or cannot capture what you're trying to get it to capture. So it's fun. You get to build in your knowledge of physics and simulation and engineering into your judgment of the model.
It's pretty cool. I think we should also link that study, because I still remember that one. I think it's still publicly accessible on the Siemens site, so we can share it with people as well. I was wondering, from your perspective, Justin, do you think an engineer will have more kind of a supervisory role later on when we get to more advanced machine learning models, kind of just having a look at the results, saying, okay, this is fine, this is not fine, we should use more data to actually train the ML model? Like, do you see there's going to be a shift less hands-on and more supervisory in that regard?
Not really. I think the paradigm shift, this is for our niche, right, of engineering simulation, which there's analytics and mainstream tech and all kinds of more applications of machine learning in the analytics world outside of just engineering simulation. But for us, I think our barrier between computer science and mechanical engineering or aerospace engineering, I think that barrier is going to continually shrink, and we're going to do more and more software development type things to leverage things in machine learning. So for example, I like what you said about, are we supervising models more so, or using them? So I think one thing that's going to be tremendously valuable, and I've seen this from firsthand experience of customer requests in the market constantly, dissemination and spread of knowledge, democratization of best practices, democratization and spread and evangelizing expert knowledge. There's only a few people in a large organization with 20 years experience, for example, in aerodynamics for compressors or whatever. There's a lot of junior engineers and mid-level engineers. How do we best disseminate that expert knowledge, those best practices, to everybody, right? And not just standard stuff that's pretty easy and topical, but like if I pull open a simulation and I have a junior, a mid, and a very senior tech fellow sit down together and all look at the same results, they're all going to look at it differently. They're all going to make different representations of the results and visualize it and do different steps to judge what's happening. So I think machine learning, in terms of supervising, and us being the supervisors in this case, I think we're going to be equipping all the engineers more with this expert tech fellow knowledge through hands-on analysis of the results, judging what's happening, maybe even changing the simulations based on what they see to run different things to make the answers better or to challenge some other design scenario. I think really what's going to happen is we're going to be leveraging, like in this case, it's a large language model based capability, right? Like a chatbot or something that would consolidate all this knowledge and then spread it. So in that case, we're going to be equipped with that sort of knowledge, and it's just going to make us more augmented. It's not going to replace some of the stuff we do. We're not going to be replaced, but we will have this in our tool belt. And I think what's interesting is when that's in our tool belt, we're describing a lot of software and architecture and things like that, and understanding how these AI models do and don't work, and deciphering the input that we're getting from it. So I think we're actually going to get more technical in some ways, more software developer in some ways, and then still remain the ones driving the design and still remain the ones doing the design decisions. I don't think we'll replace too much.
Hmm.
That's one take.
Yeah, some people definitely see it different. Some other guests we had on the
Yeah.
show for sure, but we'll see what the future brings for sure. Um, let's say you would be like going a couple of years back when you first started using AI for, let's say, CFD, for example. Like, how would you take a different approach right now? Would you use different learning resources? Is there, quote unquote, a shortcut to actually get into ML and optimization for CAE/CFD?
I probably wouldn't even bother learning machine learning. I think I would just invest everything in NVIDIA and then retire. No, I'm just kidding. Um, it's a good question, but it's kind of weird because my first professional experience with AI was in 2017,
Hmm.
which is a long time ago, and it's much different than in terms of, you know, proliferating your career into AI in 2017, 2018, 2019, 2020. It's very different than now in 2024 and 2023. So if I had to start over now, what would my advice be? I would start out with some generic learning of concepts and fundamentals of machine learning. A Coursera class for machine learning specialization is probably the best one to date to do. So I would start there, take 1 month to learn general things about machine learning.
Hmm.
Then I would start learning engineering, CAE, mechanical, aerospace specific things in machine learning. There's few resources that are out there now that can kind of take all the topics in machine learning and kind of filter them down to some of the methods and technologies that are most supportive of like really key use cases. So now you've kind of narrowed down the field of what you want to focus on for your world of now mechanical and aerospace engineering, for example. And then after that, I would spend 1 month reading literature. A lot of people probably listening to this went to grad school. Just do what you did in grad school when you first started. Read at least a paper a day, ideally much more. You don't have to read every paper, every word, every line. Some you can, glean the main conclusions. Some you want to read every line, but you shouldn't give every paper your same attention, only the best ones that are fitting for you. And when you do that, you're going to basically explore state of the art in different use cases, different areas. Do you want to focus on turbulence modeling? Do you want to focus on design work? Do you want to focus on the manufacturing and industrial and factory side? Where do you want to focus, and then learn the most relevant methods and AI or ML techniques that support that. You're not going to be an expert. Like if it's, for example, in something that graph neural networks are currently the best on. You're not going to learn everything about a graph neural network, but you'll at least learn that that area is interesting to you, and graph neural networks are the modern approach. And at the end of that 1 month or so, you should be pretty equipped. You'll have some fundamentals. Well, the full thing takes more than a month, but when you finish the literature review for a month, you'll have it narrowed down on kind of like the area of machine learning that you need to develop and how you want to apply that to mechanical or aerospace engineering. And to me, that's specific enough to where you can start building up a portfolio. So then you can start doing, free computing on Google Colaboratory or Kaggle and notebooks on their GPUs. You can find data sets that exist to support your projects and start very, very basic with very simple hands-on machine learning projects. And then just keep learning and stepping towards what you read in those papers, towards a graph neural network in that example we gave. So, the courses will probably take you a month or two. The things out there to tailor it to machine learning and mechanical and aerospace specifically will probably take you about a month. The start of the literature journey will take about a month. So somewhere around the 6 month mark, you'll start to feel like it's making sense. It takes a long time to do projects, but it makes sense. You're starting to be able to do things. And then I think that's where you can be your own guide on what to do next and start doing more complicated and high fidelity sort of machine learning projects. So it's a bit different when I started than now, but that's how I would start now if I hit the refresh button and start it over today.
Probably also get your book, which we'll talk about, by the way, next week. So everybody who wants to check it out, it's available on Amazon, if I'm not mistaken. Only on Amazon, right?
Correct.
Okay, we'll talk about that one next week. Any big changes coming in terms of ML for optimization problems in the future? Any predictions you want to make?
Yeah, I think it's just going to be more, machine learning is going to be more central and nested into our processes that involve optimization and simulation-based optimization, for example, as well as this concept of exploring through DOE or design exploration vast spaces. Because really it's like this cascade. I'll do my optimization to find the best designs. Machine learning can help there, how I described. Then I take that best design and explore a ton of scenarios to ensure that my optimal design is safe under all conditions possible that this thing I manufacture might incur. Machine learning can help there. Finally, the part we haven't talked about, but I think it makes perfect sense as the third step, is throughout that process, I'm describing running hundreds or thousands of cases from a machine learning surrogate or from simulation, right? I can't look at, graphical figures and contour plots for thousands or hundreds of cases. So this entire thing is really hinged on probably analysis and results that are single numbers, pressure drop, mixing coefficient, drag coefficient, etc. But once I have key designs and key points that I really are interested in, I want the full three-dimensional field of the continuum. I want the stress field, the flow field, whatever it may be. I want the full results, because capturing it in a single number is not enough. So machine learning is great at that. Spatial field predictions for any type of simulation, we know machine learning is getting more and more proficient at that and has been for some years now. So essentially, once you do have these key points, but you only have like a drag coefficient as the result, you can get the rest of the results for free with this machine learning based model that could train on your simulation data and then predict the field results from there. And a really beautiful end to this cascade is once you get to that point, you can run high fidelity simulations to validate what you've seen so far from the machine learning predictions. So this entire process has involved some level of simulation and machine learning, but if you spend at the end the high fidelity simulations there, you're effectively using them. You're not wasting them on crappy design points or points that are not feasible. You're really judiciously using them on the cases that matter. And upstream, how you got there efficiently and very rapidly was with ML-based surrogates and more industry workhorse simulation like eddy viscosity models or something like this. So I think what's on the horizon is that our processes in design work will be more and more machine learning based on that. And to summarize again, it's optimization, and then it's exploring vast spaces, and then it's making these surrogates that can upscale and give you full fidelity sort of spatial field results. And it's exciting because this is not, a lot of these things are not requiring new scientific machine learning algorithms that are extremely complicated, that require GPUs with 60 gigabytes of memory. I mean, these are more simple established methods, and we're the bottleneck as engineers, integrating it into our processes today, and spending time to vet and convince ourselves that these things work. It's not as simple as linear regression, but it's not as complicated as a gigantic, large language model. It's nowhere near that complicated. So I think it's a really bright future for this, and it should be pretty easy to get more and more buy-in, and the benefits, as I described, are immense. I mean, you're running simulations in 30% faster, or running optimization cycles in 30% faster, or you're getting, in that case for the chemical process industry, we made a surrogate that could predict thousands, like 2,000 points in the design space in 5 minutes. Like, it's just insane.
It's
the
crazy,
value is really, really high.
Yeah, absolutely. Because we talked about a little bit about HEEDS. Obviously, you're sitting at the source. Like, who should actually get his hands, quote unquote, dirty with HEEDS, and when does it make sense to use such a tool in the first place?
Well, the good news is that when we imagine the persona using HEEDS, in terms of introducing them machine learning features. We don't want them or expect them to be machine learning experts. So anytime you're doing an optimization study, HEEDS is an excellent choice. And you can use it with all kinds of software. It doesn't even have to be Siemens software that you use to do the optimization. It can work with all of our competitor software. It can work with text files. It can work with almost anything. So if you're this person doing optimization, HEEDS is a great choice. And if you want to use some of these machine learning based things that I've talked about, those will be in HEEDS with only clicking 5 times to set up any of those steps. You don't have to be an expert. Things are guided with wizards and behind the scenes decision making on some of the complicated technical pieces. So you have very low level information that you have to input, and it should be very, very approachable to anyone, even if you don't know what machine learning is. It should still be usable. Because like I said, we see this as really what is necessary to benefit the market. We made it an advanced ML tool with coding. It's not really helping anybody.
Yeah, absolutely. Maybe we could have kind of a deep dive session where you can kind of walk us through like how to get started with HEEDS, but I think it's probably going to be super quick, so I'm not sure if this is going to be a 1 hour session. There's probably a couple of minutes and that's it. But yeah, definitely something. If people are interested listening to this podcast, drop us a comment and let Justin and me know if you want to see kind of a hands-on deep dive series on HEEDS. But yeah, any closing remarks, Justin, to wrap it up for today's session?
No, I think we hit a lot of stuff. That was really the main points. What you just said about follow-up, I guess I just encourage people to follow up, because everything we talked about today is public publication, conference proceeding, blog article. So these are made to share. If they're interesting, ask. We will share.
Sounds good. With that, thank you so much, Justin, and see you next week then for the third part, talking about your amazing book. Cheers.
Thanks.